true? Well, we just got done talking about differentiation with the natural log function, so of course now we're going to be talking about integration. So the natural logarithmic function, integration, integrating functions with the natural log function in it. Well, let's take a look at the differentiation. So the derivative with respect to x of the natural log of the absolute value of x, and we're just putting the absolute values around that x now to remind you, of course, you can't take the natural log of a negative number. And we're going to be talking about the integration process because we're going to be integrating basically the function 1 over x, which has a domain of all real numbers except x cannot equal to 0. So we're adding this bit in. I didn't add the absolute value symbols there when we initially started talking about finding the derivative of these natural log functions, but because we're talking about integration, I'm just going to emphasize that a little bit more. And that's equal to 1 over x. Now, we don't always, of course, have just a simple x inside of our function, so we talked about a lot of u substitutions and included that with our examples, so we'll be looking at that with the integration as well. The derivative with respect to x of the natural log of the absolute value of u, again, setting up that u substitution, is equal to 1 over u times du over dx, or the derivative of u with respect to x, and that simplifies to just u prime over u. Okay, well that's review, right? So now we're going to be going in the opposite direction. Logarithmic rule for integration. Well, let u, because we're basically going to be doing u substitution with all of these problems, they're not going to just be all, 1 over x, so let u be a differentiable function of x. And, well, this isn't set up for the u substitution, but the indefinite integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. Again, of course, here we have the domain of all real numbers except x cannot equal 0. We don't have that same domain for the natural log, so we put the absolute value sign in there to make sure we are taking the natural log of positive values. And with your u substitution, and we have the indefinite integral of 1 over u du is equal to, of course, the natural log of u, the natural log of the absolute value of u plus c. Now, since we can write, or since du is equal to u prime dx, we can also maybe want to recognize that when we go to find an indefinite integral and we notice that the numerator is the derivative of the denominator, or that we have u prime over u, well then if you recognize that pattern as you're doing your work, it might be a little bit difficult to do that at first, and you can write that as, again, of course, natural log of absolute value of u plus c. As we go through my 8 examples, going from easy to increasing difficulty, as I do my u substitutions, most of the time I'm going to be striving to get this 1 over u du pattern, but again, if you recognize that u prime over u, you're talking about the indefinite integral of that being the natural log of u, absolute value of u plus c. Steps of integration. Well, these aren't going to just all be like, well, okay, let's first start with the first one here. Know your integration formulas. You're starting to get a lot of them now. Actually, when we got finished with all our rules for finding derivatives, especially with trig functions, we got a whole list of integration formulas for trig functions going in the opposite direction. Well, now we're going to get a few more in this section, and they're starting to pile up. You need to work on those flashcards, make sure you get them memorized. So far, we've looked at the power rule, which I'll put up here for a second to remind you, the log rule, voila, right there, and all your trig rules. Now, I don't have our trig rules up here, so let's pause and get that, because if I move right now, all the chalk's going to fall off. Voila, reminder, the power rule for integration. The indefinite integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1, but of course we've discussed when we talked about setting up for finding derivatives of natural log functions or functions with natural log within them, that of course n cannot equal negative 1 because we'd be dividing by 0. Now here we have our 6 basic integration rules for trig functions. The indefinite integral of sine u du is equal to negative cosine u plus c. That looks familiar because we learned about the derivative of cosine of x was equal to negative sine x and such not. So these are going to, first two are going to look familiar. The indefinite integral of cosine of u du is sine u plus c. The indefinite integral of tangent of u du is equal to negative natural log of the absolute value of cosine of u plus c. We have the indefinite integral for cotangent, secant, and cosecant here as well. I don't want to read all those off to you. Now, these aren't the only 6 integration rules or formulas that you have for trig functions, like the derivative of tangent of x was equal to secant squared x. So the indefinite integral of secant squared x is equal to tangent of x plus c. So these are your 6 basic integration rules for trig, but they are not all of them. So again, these are, if you don't know these, and I'm sure your teachers are making you or requiring you to memorize these, you want to miss test questions simply because you didn't make some flashcards or some effort to memorize all these integration rules that you are starting to get. And there are going to be a lot more by the time we get to the end of this chapter. Let me get this out of the way. Okay, so got that out of the way. Get to know those integration rules, those integration formulas. Second thing, well, you need to know them because you're going to be, well, looking at some complex problems, and you need to recognize which of those rules is going to apply to the problem in which you're trying to find the integral of, or you're trying to integrate. So identify the similar integration rule and use U substitution to get your integrand to match or conform to the rule that you think works for that problem. When you get a match, you can apply the integrand, or the integration rule, and then get that final answer, and then substitute the original variable of your problem back in, or undo that U substitution to write your final answer. Now, if U substitution is not enough, remember your trig identities. Maybe your most basic Pythagorean identity, like sine squared plus cosine squared equals 1. Maybe that will help you get your integrand to match one of those integration rules or formulas for your trig functions to be able to finish the problem. Maybe you'll have to do some long division. We'll be doing one of those in our examples. Or maybe you need some multiplication, division, or addition, or subtraction of some of the same quantities to, again, make your integrand match the rule that you're going to try and use, of course, to do that integration. Okay, well, clearly, with all these steps and, trying to get them to conform, we need some examples, and that's why you're getting so many of them in this video, starting right now. So of course, going from, our easiest example first to our hardest one, we have the indefinite integral of 3 over 3x minus 5 dx. Now, one of those rules or formulas I just gave you for integrals with indefinite integrals with natural log functions, you might look at this denominator and notice that the numerator is the derivative of the denominator. So actually what we're already looking at here is a u prime over u dx. So really, if you recognize that 3x minus 5 acting as our u value and our u prime being the denominator, you could actually just write the answer right now. But to do this process in small incremental steps, and especially if you didn't recognize that u prime over u pattern, then we would look at this and go, okay, well, the numerator is very simple, the denominator has more going on. So we have, let's just go ahead and let u equal 3x minus 5. Well, then du is going to be equal to the derivative of 3x minus 5 with respect to x is just going to be 3. And then because we're setting this up, of course, to rewrite this integrand, it's going to be 3 dx. Okay, now, again, shooting towards that idea of setting this up as the indefinite integral of 1 over u du, we have a 3 dx right here, and 3 dx, and I guess maybe just for really small, getting this broken down into really, really small steps, I can write this as 1 over 3x minus 5 times 3 dx. And then, just moving that 3 off to the side. And clearly we can see that that 3 dx can be rewritten or replaced with just simply u. Or excuse me, not u, but du. Well, 1 over 3x minus 5, we let u equal 3x minus 5, and so that's going to be 1 over u. And now again, in small steps, we see that indefinite integral of 1 over u du is going to be equal to the natural log of the absolute value of u plus c. And that is going to be equal to, after we undo our u substitution and put that references of x back in, we have the natural log of the absolute value of 3x minus 5 plus c. If your expression inside the natural log function is such that it cannot be equal to or cannot become a negative value, then you can leave out the absolute value sign and just say the natural log of 3x minus 5. But of course, there's many values of x that can turn or allow this expression to equal a negative value, so we need to keep that wrapped up in parentheses. And of course, don't forget your plus c as we do this indefinite integration, representing this is a family of functions whose derivative is equal to 3 over 3x minus 5. We'll do one of our examples near the end of the video where we solve a differential equation. Basically, I'll be giving you a point where this function passes through, which will allow us to find this unknown constant at the end of our answer. Over here, we have a little bit more going on. Now, keep it in that idea of, say, looking at that original pattern of finding that u prime over u. Now, sometimes finding that proper u substitution to get our integrand to match one of the integration rules can be a little bit challenging, but we have a basic polynomial in the numerator and denominator, and remembering that one of the patterns we can recognize is that u prime over u, or that the numerator is a derivative of the denominator. Well, when you apply the power rule for derivatives, like the derivative of x to the fourth is going to be 4x cubed, that power is going to reduce by 1. So looking at the numerator exponents in this particular case, and they're all less than the exponents or that we have in the denominator, I'm pretty sure it's a safe bet to say, let's just go ahead and let that denominator be our u and see what happens. So let u equal x to the fourth plus 3x squared. So then du is going to be equal to 4x cubed plus 6x dx. Okay, well that's almost what we have in the numerator. Now there's a couple of ways we can approach this. If I want to go after that u prime over u pattern, well, my numerator has all these coefficients are just half of what we have over here, so I can do one of two things. I can multiply the numerator by 2 and get 4x cubed plus 6x over x to the fourth plus 3x squared dx. Now, I can't just multiply my integrand by 4, or excuse me, not 4, but 2, because I've just made it twice as big, so I need to balance that out. So I can then bring out a 1/2, and sort of that 2 that I multiplied through the numerator, and that multiplication of 1/2, or that 2 over 2, reduces, of course, to 1. So I'm just making my integrand look different. I'm not changing its value. So I multiplied the numerator by 2 and then left a 1/2 out front to balance that out. And now I've got that u prime over u, and you could just write the answer at this point. But I'm going to, with most of these examples, especially as they get harder, I'm finding it simpler to look for that 1 over u du pattern. So that's an option, and really, we could move on and just have the answer, but if I'm looking for that 1 over u du pattern, and I recognize that all of these coefficients are twice as big as these coefficients, well, another way to deal with that is to divide both sides of this equation I have here by 2. And I get 1/2 du is equal to, 4 divided by 2 is 2x cubed plus 3x dx. Now I'm not going to separate this off like that. So I'm ready to do my substitution and remove all my references to x. So 2x cubed plus 3x, 2x cubed plus 3x dx, so that is equal to du. Okay, well, it's not really equal to du, right, because I have a 1/2. I'm going to put that in front of my integration symbol. And then, so that's 1 over, because I do the substitution of taking this expression out and putting in 1/2 du, doesn't mean that the denominator all of a sudden just sort of floats up into the numerator. So it's still 1 over, and then x to the fourth plus 3x squared is u. And voila, I have the indefinite integral of 1 over u du. Now that is equal to 1/2 the natural log of the absolute value of u. And as you do these problems more and more, you would probably at this point just be writing your answer. I'm doing this for teaching purposes. Plus c. And then I can take my u out and write my final answer, which is 1/2 the natural log of the absolute value of u, which is x to the fourth, plus 3x squared plus c. Now, this term has an even power, this term has an even power, so even if I allow x to be a negative number, that negative is going to be canceled out, and between these two terms is a plus sign. So really this expression is never going to be negative. So depending on how your teacher's wanting you to write the final format of your answer, you can just, because this expression never can be negative, just go ahead and write 1/2 the natural log of x to the 4th plus 3x squared plus c. Now, I want to back up here just for a second, and why am I, this is 1/2 this integrand. Now, when I do the indefinite integral of 1 over u du, it's natural log of u, absolute value of u, plus c. There's actually two terms, so why am I not, and really, maybe I should, because it's always good practice to include parentheses every time you do basically a substitution, if you will, to make sure that that 1/2 or whatever coefficients we have in most algebra work that we do gets distributed to those parentheses. Well, 1/2 of natural log of the absolute value of u is 1/2. Well, I got the u out now, and then 1/2 times c. Well, I don't know what that constant is, but when I multiply it by half, I'm just going to get another unknown constant, and there's no need to write that 1/2 c over here. So really that 1/2 is getting distributed through these two terms, but it still just shows up as a plus c. So there's our first two examples. Let's get on to the next one. I was going to say I said 2, but then I saw what I was doing in my next example. Didn't want to cram it all up on the board, not have enough space. So we have the indefinite integral of 3x squared plus x minus 1 over x plus 2 dx. We're going to have to fiddle with this one, because if you think of the one of those rules that I gave you, the indefinite integral of u prime over u dx is equal to the natural log of u. Not that everything we're going to do is natural logs, of course, but you can't have u prime over u. Think about finding derivatives. When you take like the derivative of u, you bring those powers down. When it's like just a basic polynomial or whatnot, you bring those powers down and reduce them by 1. So our numerator having a degree that's greater than the denominator is going to be a problem. So to get this integrand to match one of our rules, and specifically for right now, we are going to be able to match the u prime over u or the 1 over u du, is long division. So we need to do this long division to rewrite this, and pretty sure by now you know how to do long division. Voila, like magic. Okay, the one little quirky thing I do with long division, I like to, for my answer up here, keep that on top of what I'm trying to match. I guess probably because of me teaching Algebra 1 and Algebra 2 and having, trying to remind kids, you are trying to get this first term to match this first term. So I kind of do that weird, because of course this is basically the second degree column. So most teachers and books would have this 3x minus 5, right here to keep all those degrees stacked. But at any rate, 3x squared plus x minus 1 divided by x plus 2 is equal to 3x minus 5. And then we have this remainder of 9. Well, don't forget, of course, you have to take that remainder, in this case a positive 9, and put it over what you're dividing by. Like 5 divided by 2 is, well, 2, but then there's another half. So it's 2 plus, or 2 and an additional 1/2. So this problem now can be rewritten as the indefinite integral of 3x plus, or minus 5, excuse me, plus 9 over x plus 2 dx. Now I have to wrap all this in parentheses to show that, I have my dx here applying to all these terms. And again, for just teaching purposes, I'm going to go ahead and split all of these terms apart just to have it in small little pieces, very, very simple, and hopefully clear to know how to do this. So we have the indefinite integral of 3x dx minus the indefinite integral of 5 dx plus the, well, at this point, I'm looking at the denominator right now, and it's x plus 2. Now, I know the derivative of x plus 2 is equal to 1. So I can either leave the 9 up there and deal with it later, or I can move the 9 in front of the integration symbol and write 9 times the indefinite integral of 1 over x plus 2 dx. Now, again, do you recognize one of the rules I gave you? If so, great, and if not, you might be doing a u substitution to make sure you really, really see it. Well, here, this is just power rule. The indefinite integral of 3x, we're going to take that exponent of the degree on that x and bring it up by 1, so we're going to have 3x squared and divide that by 2 because we're going to divide by that power increased by 1, minus 5x plus, okay, now the 9. Well, like I said, you might be able to just write the answer, or you might still, because you're just starting into these kind of problems, need to go, okay, well, let's see here. Hopefully you can see the yellow from the white. U is equal to x plus 2, so then du is going to be, well, the derivative of x is 1, 2 is a constant, so it's just going to be 1 dx. So u is, well, I just said it, x plus 2, I'm sorry about the hesitation there. So 1 over u, taking the x plus 2 out, plugging in the u, dx is equal to du. Oh, okay, I see it now. 1 over u du, or u prime over u dx. At any rate, our final answer is going to be 3x squared over 2 minus 5x plus 9. And I'm going to go ahead and just write the answer. The natural log of the absolute value, I'm going to go ahead and at the same step put that u back in and get x plus 2 plus c. And this expression can become negative, so of course we're going to keep that absolute value sign around there. And voila, that's the end of our next example. So let's get to another one. For our next example, we have the indefinite integral of 3x over the square root of 16 minus x squared dx. Well, we have a lot going on in the denominator, and inside that square root function, that inside function, it seems like that would be a good place to start looking for a u substitution. So we're going to let u equal 16 minus x squared. That means that du is going to be equal to negative 2x dx, bringing that power down and reducing it by 1. And we have a x dx, but there is a 3 in front instead of a negative 2. So what I'm going to do is, I'm going to go ahead and bring this 3 up front. Okay, so if I can get this x dx here, then I have a substitution. So I'm going to divide both sides by negative 2. And now I have a substitution and remove a couple of these references to x and just have the du in there. And I'm going to have this 1/2 out front. And actually, 16 minus x squared is right here, so I have enough to complete my u substitution and get all the references of x out of here. And this negative 1/2 is going to come out front. We have negative 3 over 2 times the indefinite integral of x dx is going to come out. I just took care of that, so just the du. So we have 1 over du over the square roots of u. Well, it's 1 over something with u, but remember, this is not the first time we've done u substitution. It's not like everything now is going to be a natural log function. So this can be rewritten as negative 3/2 times the indefinite integral of u to the negative 1/2, just writing this as a fractional exponent and getting the u out of the denominator so I can see more clearly that the use of that power rule. And so we're going to have negative 3/2. We're going to take this exponent and increase it by 1. And when you raise that power by 1, you then have to divide by that value. So that 1/2, well, now we're going to divide by 1/2 plus c. And maybe you just write the answer already, because you know when you divide by a fraction, you're multiplying by the reciprocal, right? So this is going to become negative 3 over 2 times, flipping that 1/2 up, 2 over 1. And we have that u to the 1/2 power plus c. Well, the multiplication of 2 and the division of 2, or the 2 over 2 cancels out being 1, and so we're just left with negative 3 The u, of course, started off as 16 minus x squared, and it's u to the 1/2 power. So I can put that u in and then also write that as a square root again. So we have negative 3 times the square root of 16 minus x squared plus c. And just to always check your work, I'm going to check by just checking my work that I've already done for planning for this. You can check the back of your book, or you can take the derivative of this and see if you get the problem you were asked to find the integration of. So is the derivative of negative 3 times the square root of 16 minus x squared plus c, of course when you take the derivative of a constant, it's 0. Does that equal your 3x over the square root of 16 minus x squared? Hope that makes sense. Let's get on to the next example. Let's find the indefinite integral of 1 over 2x times the natural log of x to the 4th dx. Well, I'm going to see what happens when I let the natural log of x to the 4th be my u. So we're going to say let u equal natural log of x to the 4th. Then before we find the du, I'm going to go ahead and take this 4 and move it out front and rewrite that as bring that power down, 4 times the natural log of x. Now, du is going to be equal to 4 times, I don't know why I'm writing over a fraction bar, but 4 times, and then the derivative of the natural log of x is equal to 1 over x. Okay, so we've got, what do we have here? Well, we've got a 1 over x, and we have dx, and we have a 1 over x and dx. So I'm going to take this 4 and divide it to the other side, and we're going to get 1/4 du is equal to 1 over x dx. And now we have a nice substitution to get rid of that reference of x. The natural log of x to the 4th we have set equal to u, and then we have this 1/2 here that I'm going to pull up front. So we're going to have 1/2 times, and then that 1/4 that we have here, times the indefinite integral of 1 over u, or 1 over x dx is du, and the 1/4 again is right there. And then we have 1 over the natural log of x to the 4th, which we set or allowed equal to u, so that is equal to 1 over u. And now we have 1/8 times the indefinite integral of 1 over u du is the natural log of the absolute value of u plus c, and that's going to be 1/8 times the natural log of u, which is the natural log of x to the 4th plus c. All right, next example. Now, to get a little more complicated, indefinite integral of the square root of x over the square root of x plus 2 dx. Okay, well again, we're just looking for that u substitution, so I'm going to again let that be the denominator, and we're going to have it be the entire square root of x plus 2. So we're going to let u equal the square root of x plus 2, which we can rewrite as x to the 1/2 plus 2, and then du is going to be equal to, let's bring that 1/2 down up front, so we have 1/2 x, reduce the power by 1, so negative 1/2 x, and then of course the constant is 0, dx. Okay, so then we have, let's go ahead and get rid of that negative exponent, rewrite this a little bit, and we have 1 over 2 square root of x dx is equal to du. Now let's see how we're going here. We have, well, we have the square root in the numerator here, and here we have the square root in the denominator. But we have the u substitution, that's x squared of x plus 2. Doesn't seem like this is quite as straightforward as the other one. Well, I just said a second ago they're getting a little bit harder. So I'm going to take this 2 square root of 2 to the other side and get 2 square root of x. I think I just said the wrong thing. 2 square root of x. Multiply that to both sides and we get 2 square root of x du is equal to dx. And let's just see where we stand. We have the indefinite integral of, well, I have nothing to get rid of that square root of x so far, so we have the square root of x we have the square root of x plus 2 is RU, and dx is 2 square root of x du. Okay, and then if I go ahead and take it, if I let that be over 1 and multiply this together, we have the indefinite integral of 2 square root of x times square root of x is x over u du. Well, I have not gotten rid of all of my references of x yet. So, and that happened when we started learning about integration, definite or indefinite, with u substitution. So sometimes we have to come up here and just work a little bit more. So right here, if we have u is equal to the square root of x plus 2, then I can take the plus 2 and move it over to the other side, and we have u minus 2 is equal to the square root of x. But I had square root of x up here, but now I've got 2x. So I need to take this and square both sides of the equation, and we get u squared minus 4u plus 4 is equal to x. Now I've gotten rid of all my, or will with that substitution, can get rid of all my references of x and complete my u substitution. So we have the indefinite integral of 2 times u squared minus 4u plus 4 over u du. Now I'm going to do a couple of things. I'm going to take this 2 and distribute it through my parentheses, and I'm also going to break this apart just to, again, get this in the smallest individual terms and make this as clear as possible. And if you can do this in fewer steps, we'll do so. But for teaching purposes, I like to show everything. So we have 2u squared over u, which is just going to be 2u. So the indefinite integral of 2u du. And then 2 times negative 4 is negative 8 u over u. So those are going to cancel out. So we're just going to have, I'm going to go ahead and put a plus sign in here. Actually, no, excuse me, minus the indefinite integral of 8 du. And then we have 2 times 4, which is 8, and it's positive. So I'm going to do plus 8, and it was because it was going to be 8 over u, so it's going to be 8 times 1 over u du. Now I can really have this in such individual small pieces. Each of those terms is a separate integral. It's kind of straightforward. We're going to raise that power. We're going to use the power rule. We're going to take that power, rise it by 1, and then divide. So we're going to have u squared minus 8u, and then plus 8, and the indefinite integral of 1 over u du, which I've said all this whole video now we know is the natural log of the absolute value u, and then of course your plus c. Now that, I'm going to start getting in the way here. I need to get my u substitution back in. So let me get this erased, and I'm going to take each of these u's out and plug in our square root of x plus 2. So taking all my references of u out and plugging back in my square root of x plus 2, doing a little bit of algebra, combining like terms, and taking my negative 12, which is a constant, and combining it with my other unknown constant, it's just going to make another constant. So maybe when you're looking in the back of your book, sometimes you're thinking, well, where'd my minus 12 or my plus 6 or whatever you have in my final answer, where do they go? Why is it in the back of the book? They're combining that with the constant c and just making another unknown constant. So we have x minus 4 square root of x plus 8 times the natural log of the absolute value of the square root of x plus 2 plus c. My next example is going to have a little bit of trig. Let's get to that right now. Find the indefinite integral of 5 minus the cotangent of a half angle theta over 2 d theta. Okay, first thing I want to do is, again, just for clarity, get it in all little tiny small steps so it's easy to understand. We're going to separate these two terms and get the indefinite integral of 5 d theta minus the indefinite integral of the cotangent of theta over 2 d theta. And really the first term there is already set. It's just going to use a power rule. But over here, I have an inside function of theta over 2 in the cotangent function. So we're going to let u equal theta over 2. And then du is going to be equal to, well, the derivative of 1/2 theta is just going to be 1/2, and then d theta. Or du, d theta. Now, okay, so I have a d theta, but I don't have a 1/2. I mean, the 1/2 is inside the function, and I've already taken care of that with this u substitution of it being theta over 2. So we're going to multiply both sides by 2 and get 2 times du is equal to d theta. Now, let's get this rewritten. We have the indefinite integral of 5d theta minus the indefinite integral of the cotangent of, and I just forgot something, right? I'm going to get rid of all my references of theta, and where am I going to put the 2 at? I'm going to move that out front. So minus 2 times the indefinite integral of the cotangent of theta over 2 is u. Now let's go back to that again. D theta to du. D theta to du. And now we have 5 theta, sorry about that, minus 2 times the integral of the cotangent of u du is the natural log of the absolute value of the sine of u plus c. And that means we have as our final answer 5 theta minus 2 times the natural log of the sine of u, which is theta over 2 plus c. And by the way, I want to highlight something here. Really, I should be wrapping this in parentheses because I'm taking this integrand out and replacing it with an expression that has 2 terms. The reason why I'm kind of skipping that, maybe it isn't that great to do so, is I'm going to distribute this -2, and -2 times c, a constant, is just going to come out to another unknown constant. And negative times positive is negative, but is that constant positive or is that constant negative? I don't know, and I'm just going to leave the plus sign in there to indicate that it's just an unknown constant. And that is their answer to our next example. We have one more example with some trig functions, so let's get to that right now. For this example, I'm just going to reveal the solution in kind of like in small steps to allow you to attempt the problem on your own. It's very similar as the other ones. Solve the differential equation. We're simply going to just say, we're going to integrate both sides and just say that s is equal to the indefinite integral of this. We're going to have that plus c. We're going to use the value of what would be theta and the resultant of the function, or s, which is going to be 5, to help figure out what that constant c is. So instead of writing the plus c at the end, we actually have, an actual equation, not a family of equations where we don't know where that vertical shift is, that constant at the end of the function. So let's find that indefinite integral. Let's take care of, instead of, which is basically that plus c, again, says we have that family of function, but find, which member of that family that actually goes to this point and thus solves the differential equation. Okay, I got one last example. It involves a definite integral. By now, hopefully, just giving you a opportunity to practice some of the skills I've shown you in this video, and also, remind you of how to find a definite integral. All right, last example, and thank you for sticking through all of these with me, and hopefully it's going to help you get to your homework as easy as possible. Okay, so we have a definite integral. We want to evaluate this integrand from 1 to e squared. So our inside function, again, maybe you might try u substitution, doesn't work it out, try again. I got a lot going on here in this power of 2, plus I also know that the derivative of the natural log of x is 1 over x, and we have an x in the denominator. So I'm thinking that we want to let u equal 2 plus the natural log of x. That means that du is going to be equal to, well, just 1 over x dx. And we do have a 1 over x. So let's go ahead and move this 3 in the denominator up front. So we have 1/3 the integral, or the definite integral, from 1 to e squared. 2 times the natural log of x is u. So we have u squared. I've just taken this 3 out front. So this 1 over x, because again, the x is in the denominator, right? So that 1 over x dx is equal to du. And I was setting up to write a fraction, but actually that 1/3 came out front. So really I could simplify this to be u squared du. Okay. How do you want to show your work? Now, see, I'm evaluating a definite integral. So because of that, this is now in reference, basically referencing u, but my lower and upper limit was from an integrand that referenced x. So this isn't really right. Maybe you could put like a little asterisk here to remind you that these are referencing or in terms of x, and now my integrand is in terms of u. Do the integration and then put it, and then take that value of u or that expression for u and substitute it back in before you evaluate the definite integral. Remember, when we talked about definite integration with substitution, again, we don't have to go back and substitute this back in if we use this equation that u is equal to 2 plus natural log of x. I can rewrite these or put these lower and upper limits in terms of u as opposed to in terms of x. And then I could just continue the problem in a much simpler manner. And so I'm just going to kind of take these out and write everything in terms of u. Not have to maybe leave them blank or put an asterisk next to them and note that, denote that they're really for a different variable. So for our upper limit, well, that's going to be 2 plus the natural log, and that upper limit was the e squared, so the natural log of e squared. Now, of course, natural log is log base e. I'm logging something with the same base, so that log base e and that base e are going to cancel out. So we just have 2 plus 2, which is equal to 4. And our lower limit is going to be, 2 plus the natural log of, my lower limit was 1, I'm putting it in terms of u basically, so again 1, we have 2 plus the natural log of 1 is going to be equal to 0, and so we have our lower limit is equal to 2. So we can come in here and put a 2 there and a 4 there, and now I don't even have to go back to my original expression to evaluate the definite integral. Indefinite integral, of course, you've seen me go do that through the rest of the video. So we have 1/3, okay? Well, this isn't a log rule, this is just power, so we're going to raise that power and divide, so it's going to be u cubed. And instead of dividing by 3, I'm going to go ahead and just show that multiplication of 1/3. So u cubed divided by 3 is the same as 1/3 u cubed. And let's put our upper and lower limit over here, indicating that we need to substitute those in. Now we have 1/3. And I'm just going to leave the third there. 1/3 times 1/3 times the upper value of 4, or limit of 4 cubed, minus 1/3 times my lower limit of 2 cubed. And we've got 1/3 times 1/3. 4 cubed is 64. So actually, instead of writing 1/3, let's write 64 over 3. Minus 2 cubed is equal to 8 over 3. That is going to be 1/3 times 64 minus 8 is 56 over 3, which comes out to be 56 over 9. Whew, okay, that's my last example. That's my answer, 56 over 9. Let's double check it. Bam, that's it. I'm Mr. Tarrou. Go do your homework.